Welcome to another lesson of Math 1314, College Algebra. Today we will be discussing Section 2.4, Complex Numbers. In this section, we will discuss adding and subtracting complex numbers, multiplying and dividing complex numbers, and simplifying powers of I. Let's get right to it. Let's start by defining what I is. Well, here's the definition. We know that the square root of any positive real number, we can do certain things to manipulate those expressions and eventually solve them and evaluate them. The difference here is that we can now find the square root of a negative number. And the way that we do that is we figure out that the square root is not real. In fact, if the value in the radicand is negative, the root is said to be an imaginary number. So the imaginary number I is defined as the square root of negative 1. The square root, root of negative 1 is I. Or the square root of negative 1 is equal to I. Using properties of radicals, I squared is equal to the square root of negative 1 squared, which is just equal to negative 1. So we can rewrite the square root of any negative number as a multiple of I. Let's do an example. In this example, we want to simplify the square root of negative 49. Well, we can rewrite the square root of negative 49 as the square root of 49 times the negative 1. Then we can separate that as two separate radicals, the square root of 49 times the square root of negative 1. And what does that give us? Well, the square root of 49 is 7, and the square root of negative 1 is equal to I. So the square root of negative 49 is equal to 7i. Let's move on and discuss imaginary and complex numbers and what that looks like in notation form and the definition of a complex number. So let's define complex and imaginary numbers. A complex number is a number of the form a plus bi, where a is the real part of the imaginary number, that's a, and b is the imaginary part of the real number, just the coefficients there. If the b, the imaginary part, is equal to 0, then a plus bi is just a real number. Now, if a is 0 and b is not 0, then the complex number is called a pure imaginary number. An imaginary number is an even root of a complex number. So let's discuss what happens when we're given an imaginary number, how we're able to express that in the standard form of a complex number. So if we're given an imaginary number, that's something that looks like negative a, the square root of negative a, where a is greater than 0. Okay, the first thing we do is we rewrite the square root of negative a as the square root of a times the square root of negative 1. Okay, then we express the square root of negative 1 as I, and so finally we write the square root of negative a times I in simplest form. Let's do an example. In this example, we're asked to write the square root of negative 24 in standard form. Our first step tells us that we need to rewrite the square root of negative 24 as the square root of 24 times the square root of negative 1. Not negative I, but negative 1. Okay? And then we rewrite the square root of negative 1 as I. So we have the square root of 24 times I. And then we're supposed to simplify the square root of 24. Well, the square root of 24 is the square root of 4 times 6 times I, which is the square root of 4 times the square root of 6 times I. Well, the square root of 4 is just 2, so we have 2 times the square root of 6 times I, and that is the simplest form that we get. That is the solution and is the square root of negative 24 in standard form. Let's talk about plotting a complex number on the complex plane. So when we plot real numbers on the number line, we only have a single component, which is the real component. But with complex numbers, we have a real part, A, and an imaginary part, B. That's a complex number in standard form. So what we need is to use the complex plane. The complex plane is a coordinate system in which the horizontal axis represents the real component, and you guessed it, the y-axis represents the imaginary component. So complex numbers are points on this plane that are expressed as ordered pairs. Those ordered pairs are very similar to numbers that we plot in the xy plane. They look like A, B, where A is the real part and B is the imaginary part. Okay, so if we have axes like this, our x-axis is the real part, and our y-axis is the imaginary part. So what if we were given (3 plus 2i), plot 3 plus 2i on the graph. Okay, so let's make some marks. Okay, so we first determine the real part of 3 plus 2i, which is just 3. So we go over 3 spots, and then we move parallel to the vertical axis to show the imaginary part, which is 2. So we go up 2. So we can plot our point there. We can plot that ordered pair Oh, I didn't go far enough over the second time. So it's 3 in the horizontal and 2 in the vertical. There's 3, 2. 3, comma 2, which represents 3 plus 2i. So let's talk about representing components on the complex plane in general. So if we're given a complex number, and then we're asked to represent its components in the complex plane, we first determine the real part, and the imaginary part. Then we move along the horizontal axis to show the real part. Then we move parallel to the vertical axis to show the imaginary part. And finally, we plot the point at that intersection. Let's do another example. Let's plot -4 minus I on the complex plane. In this example, we need to first identify the real and imaginary parts. So -4 minus I, our real part A is -4, and our imaginary part I is -1. So the ordered pair that we need to plot is -4, -1. So we move, I'm going to pull up the pointer here. We start at the origin and we move on the horizontal axis 4 spaces to the left to represent the real part, and then we go parallel to the y-axis and go down 1. So I'll go and mark that, and we'll plot that point right here. That's -4, -1. And that's how you plot a number on the complex plane. Let's move on to discuss adding and subtracting complex numbers. Just like with real numbers, we can add and subtract, multiply, and divide with complex numbers. Let's first start with addition and subtraction. So the way that we add a complex number, let's consider 2 different complex numbers, a plus bi plus c plus di. The way we add those complex numbers is we add the real parts, a plus c, and then we add the component imaginary parts, b plus d. So we add the component real parts and the component imaginary parts. What about subtracting? Well, it works the same way. If we have a plus bi minus c plus di, then we just subtract the component real part, so a minus c, plus the difference in the imaginary parts, b minus d, times I. So how do we do it? We identify the real and imaginary parts of each number. Rewrite that. Then we add or subtract the real parts. And finally, add or subtract the imaginary parts. Let's try an example. In this example, we're asked to subtract 2 plus 5i from 3 minus 4i. Which number do we start with? Well, we need to start with the 3 minus 4i and then subtract the 2 plus 5i. So we need to first identify the real and imaginary parts of each number. The real part of the first number is 3, and the real part of the second number is 2. So we can rewrite that as 3 minus 2. And then we need to subtract the imaginary parts. The imaginary part of the first number is negative 4. And the second is 5. So we have negative 4 minus 5 times I. Well, we have 3 minus 2, which is just 1, plus negative 4 minus 5 is negative 9 times I. So the result of this difference is 1 plus 9i. It works just like regular addition and subtraction. You just have to do the real and imaginary parts. So it's really a two-step process. Before we start multiplying complex numbers by complex numbers, let's first discuss multiplying a real number and a complex number. If we multiply a real number by a complex number, all we have to do is use the distributive property and simplify. So let's consider an example. Let's find the product of 1/2 times 5 minus 2i. Well, all we need to do is use the distributive property. We can multiply the 1/2 times the 5. That gives us 5/2. And the 1/2 times the negative 2. That gives us a negative 1i. So finally, we're left with 5/2 minus I. So all we did was multiply the real number times the real part, and then the real number times the imaginary part of the complex number. And we'll find very similar things when we multiply complex numbers together. We end up having to double distribute like we would with a binomial, and we'll discuss that shortly. Multiplying complex numbers together. If a plus bi and c plus di are complex numbers, then their product is as follows. A plus bi times c plus di gives us, we need to distribute, we have a times c plus a times di. Then we have bi times c and bi times di. Okay, so what that tells us is that we now have some more real stuff and some more imaginary stuff that we need to combine, like terms. Well, we know that we can rewrite this as AC plus ADI plus BCI plus B times D times I squared, I times I. Well, what is I squared? Well, I squared is just negative 1, so we can rewrite it as AC plus ADI plus BCI plus, actually we'll just change that to a negative now, minus, because I squared is negative 1, minus BD. Okay? And then what we can do is we can group our real parts and our imaginary parts, AC minus BD, plus the imaginary parts AD plus BC, all times I. And that's grouping the real, these parts, and the imaginary parts. And that's how we get the product of two complex numbers. So in general, we distribute, which I would call double distributing, like with binomials. Rewrite that. And then recall that from the definition of I squared is equal to negative 1. And finally, group the real and imaginary terms from the product. Let's try an example. In this example, we'll multiply two complex numbers together. We have 3 minus 4i times 2 plus 3i. So we'll first rewrite those so we can distribute. So we first distribute the 3. 3 times 2 is 6. 3 times 3i is plus 9i. Negative 4i times 2 is minus 8i, and negative 4i times 3i is minus 12i. Well, negative 12i is plus 12 because I squared, it should be I squared, not I. I squared is negative 1, so we'll rewrite that just so we can see it. Because I squared is equal to negative 1. So we have 6 plus 9i minus 8i. Negative 12 times negative 1 is plus 12. Then we can combine the real parts, 6 plus 12, and the imaginary parts, 9 minus 8 times I. So we get 18 plus 9 minus 8 is 1. 18 plus 1i, or 18 plus I. And that's our final answer. Let's move on to discussing dividing complex numbers. So we've saved dividing complex numbers for last for more than one reason, but mostly because dividing two complex numbers is more complicated than any of the other operations we've done, because we cannot divide by an imaginary number, meaning that any fraction must have a real number denominator to write the answer in the standard form a plus bi. So the only way that we can multiply the numerator and denominator to eliminate that imaginary portion in the denominator is to use the complex conjugate. The way we find a complex conjugate is by changing the sign of the imaginary part of the complex number. So if we have a complex number a plus bi, its complex conjugate is switching the sign on the imaginary part, a minus bi. So we always multiply by a complex conjugate when we're dividing by complex numbers. So how do we know that this ends up being real? Well, we can distribute to prove it. A times A is A squared. A times a negative BI is minus ABI. BI times A is plus an ABI. And then you have BI times a negative BI minus B squared I squared. We can combine those terms. We get A squared. The minus ABI plus ABI cancels out, and we're left with minus B squared I squared. Well, I squared is just negative 1, so we have A squared minus B squared times negative 1, which leaves us A squared plus B squared. Well, A squared plus B squared is a real number. So what we can do now is consider the following. Consider complex numbers C plus DI divided by A plus BI, where A is not equal to 0 and B is not equal to 0. Then we get where we multiply by the complex conjugate of whatever our denominator is. Well, our denominator in this case is A plus BI. So to simplify this, we need to take C plus DI over A plus BI times A minus BI over A minus BI. So we have to perform those multiplications in the numerator and the denominator. Well, we know in the denominator, what will we get? Well, we just did that work. We'll get A squared plus B squared. In the numerator, we get C times A, or AC. C minus BI, C times minus BI is minus CBI. DI times A, or ADI. And then DI times negative BI is minus BDI squared. Okay? And then remember that I squared is just equal to negative 1, so we can rewrite this as AC minus CBI plus ADI minus BD times negative 1, all over A squared plus B squared. And then we can simplify a little further by combining the real parts and the imaginary parts. That's AC plus BD, that's the real part there, plus AD minus CB times I, all, we'll rewrite that denominator, all over A squared plus B squared. And so that shows us how we divide complex numbers. So let's do the definition of the complex conjugate. The complex conjugate of a complex number A plus BI is A minus BI. The real part doesn't change here. We just change the sign on the imaginary part. Let's find some complex conjugates. Find the complex conjugate of -3 plus 4i. So how do we find the complex conjugate? Well, we just change the sign in front of the imaginary part. So the complex conjugate is -3 minus 4i. What if we had -1/2 I? What's the complex conjugate of that? Well, notice that the real part is 0. 0 plus a -1/2 I, or 0 minus 1/2 I. So we just changed the sign on the imaginary part, so the complex conjugate would be 1/2 I. Now let's discuss the steps in dividing complex numbers. If we are given if we are given two complex numbers divide one by the other. Our first step is to write the division problem as a fraction. We then determine the complex conjugate of the denominator. Then we multiply the numerator and the denominator of the fraction by the complex conjugate. Of the denominator. And finally, we simplify the expression we get. And that's how you divide two complex numbers. Let's do an example of that. For this example, we want to divide 2 minus 3i by 4 plus 3i. So what's our first step? We need to rewrite it as a fraction. So 2 minus 3i over 4 plus 3i. Our next step is to multiply the numerator and the denominator by the complex conjugate of the denominator, which we have to find. What is the complex conjugate of 4 plus 3i? Well, that's 4 minus 3i. Okay. So we can do the distribution in the numerator and the denominator. Well, let's do the numerator first. 2 times 4 gives us 8. 2 times a -3i is minus 6i. -3i times 4 is minus 12i. And -3i times -3i is plus 9i squared. That's our numerator. Let's do that one more time. Okay, in the denominator we get 4 times 4, which is 16. 4 times negative 3i is minus 12i. 3i times 4 is plus 12i. And 3i times a negative 3i gives us a negative 9i squared. Okay, so in the numerator we get 8 minus 6i minus 12i plus 9 times negative 1. That's what I squared means. In the bottom we get 16 minus 12i plus 12i minus 9 times negative 1. Okay, we can simplify a little further. In the numerator, 8 minus 6i minus 12i is 8 minus 18i minus 9 all over 16 minus 12i plus 12i. Those cancel out. So we have 16 plus 9. And then 8 minus 9. Sorry, 8 minus a negative 9. No, that's not right. 8 minus 9 is negative 1 minus 18i all over 16 plus 9, which is 25. Can we simplify this any further? How do we want our answer to look? Well, we can rewrite it as real and imaginary parts in standard form. So we have negative 1 over 25, which is the real part, minus 18 over 25i. Can we simplify 18 over 25? We cannot. That is all we can do there. So in standard form, the answer to this division problem is negative 1 over 25 minus 18 over 25i. The last concept in this section that we need to discuss is simplifying the powers of I. Now, something that we need to note is that the powers of I are cyclic, which means that they follow a cycle. So let's see what happens as we raise I to increasing powers. Well, I to the first power is just I. What is I squared? Well, I squared is negative 1, as we've seen. What about I to the third power? Well, that's equal to I times I squared. Don't you agree? Which is I times a negative 1, or negative I. And then I to the fourth is I times I cubed, which is I times a negative I. And what does that give us? A negative I squared. Well, what's negative I squared? Well, that's the negative of negative 1. Well, negative of negative 1 is just 1. So let's rewrite that one more time. I to the first power is I. I squared is negative 1. I to the third power is negative I. And I to the fourth power is 1. So what happens when we get to I to the fifth power? Well, that's just I to the fourth power times I, which is 1 times I, or I to the first power. So every time we go through through 4 powers, the cycle repeats to give us I, negative 1, negative I, 1 for every 4 powers. So something we will want to do is to factor out as many factors of I to the fourth as possible when we're looking at something that has a lot of a high exponent, high power on I. We want to factor out as many 4s as we can because I to the fourth power is just equal to 1. Let's consider an example. For our final example of this section, we want to evaluate I to the 18th power. Again, remember that I to the 4th power is equal to 1. So we want to factor out as many factors of I to the 4th as possible. So we need to figure out how many times 4 will go into 18. Well, the nearest multiple of 4 is 16. So let's rewrite I to the 18th as I to the 16th power times I squared. That gives us a total of 18 factors of I. Well, we can rewrite I to the 16th as I to the 4th raised to the 4th power times I squared. Well, I to the 4th is just 1, so we have 1 raised to the 4th power times I squared. Well, 1 to the 4th power is just 1 times I squared, which leaves us with I squared. What do we know that I squared is? Well, I squared is just negative 1. So what did we find? So I to the 18th power is just negative 1. And you could use a similar technique for any power on I to figure out which stage in the cycle of the powers of I you have. That concludes section 2.4. If you have any questions, feel free to reach out to me via email or come by my office hours, and I'll be glad to help you.